In this example, we'll consider a vector subspace, which is a subset of R3 subject to a condition on the points. What we'd like to do is show that we have a basis, and then we're going to lead into what's the dimensionality of that subspace. But first, let's talk about the basis properties. So, to show that this set of vectors, v1 and v2, is a basis for specifically v here, we need to show two things. Again, bases have two properties. One, that this set v1, v2, those two vectors, is linearly independent. And we need to show that the set v1, v2 is a spanning set, or a generating set, for the space we're talking about, for v in this case here. So we'll just work on these one by one. Fortunately, v1, v2, which is equal to the set 1, 0, negative 1, and 0, 1, negative 1, is only two vectors. And because it's only two vectors which are not multiples of each other, that means that they are linearly independent. If we have a two-element set, linear independence is really easy to check. Sorry, the set is linearly independent. Done. So property 1 here is proven. Notice if we'd had 4 vectors, we'd have to do something more complicated, but here it's just 2 vectors, so we can take this shortcut. Step 2, the spanning set. Well, what does that mean? It means that v1, v2, let's put this as a claim. So our claim is that v1, v2 spans v. And what does that mean? It means that any element of v is a linear combination of those two vectors, v1 and v2. So how do we prove that? Well, what we have to do is grab an arbitrary element of this vector space v. So what would that look like? Well, to be in v, a point x, y, z satisfies x plus y plus z equals 0. So it's an element of R3, but it has this extra condition on it. But that also means, or we could rewrite it as z equals negative x, negative y. And what that means is that every element in v has the form x, I can pick whatever I want, y, I can pick whatever I want, but then the z, or the third component, must follow this form here. My z component, my third component, must equal negative x, negative y. Now, can I find that element of v as a linear combination of v1 and v2? Just tidy that up a hair there. I think we lost our 1, or the comma. So, given this target, can we build this vector here, or any element of this shape, or this form, based on, let's call it a times v1 plus b times v2 equals xy, negative xy, oops, negative x, negative y, for all x and y. If you give me x and y, can I find a and b as a result? Well, absolutely we can, because we're actually given the definitions of v1, v2. v1, v2. So that's a times, the vector v1 was up here, 1, 0, minus 1. 1, 0, minus 1. And b was 0, 1, minus 1, so just a 1 in a separate slot. X, y, and minus x, minus y. And if we start solving, given x and y, can I find AB? I have to keep the direction clear. But if I look at the first component, we get that A plus no B's equals X. Oh, okay. And what about the second component? Well, it's 0A plus B has to equal Y. Okay, so that's fine. I know what A and B are. And then I can check the third component. And if I try to check that, I would get A times minus 1 plus B times minus 1, which I'm claiming from these two solutions here is the same as X times minus 1 plus Y times minus 1. Well, that's equal to minus X minus Y, which does equal the target value here. And so for any x, y, minus x minus y element of v, we can find an AB such that, AB element of the reals, our scalar multipliers here, such that AV1 plus BV2 equals that xy, negative x, negative y, which implies that V1, V2 spans V. So notice the logic again. We have to pick an arbitrary point in the set and show that we can reach that point, reach that vector, through a linear combination of the given vectors that we had. Next up, use that result to determine the dimension of V. Well, the dimension of V is equal to the number of elements in any basis. And the basis for V, we just found that V1, V2, which was that specific set of 1, 0, minus 1, and 0, 1, minus 1, is a basis for V. And so, hey, there's two things in it. That set contains two elements, therefore V is two-dimensional. And that matches our idea of this, because this is a plane in R3. The fact that it's in R3 is somewhat relevant, but more importantly, it's a plane, and our intuition tells us that planes in 3 dimensions are a two-dimensional subspace, and that's what we've just confirmed with our calculations here. Now, to change gears a bit, can we use that idea of basis to, not prove, but give an indication that C infinity is infinite? Well, if you've taken series in calculus, you would have found this Taylor series or power series, this famous one for e to the x, which is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial. And the important thing is there's a dot, dot, dot at the end of that. And so if we think about how we built a basis for polynomials, well, the basis for C infinity here, I should mention that e to the x is in C infinity, so it's one representative member of it. And so a basis for C infinity has to have constants in it, it has to have x's in it, it has to have x squareds in it, it's going to need x cubes in it. In fact, it's going to need all the powers of x, but we'll never be able to stop at any finite power of x. We're going to need an infinite number of powers just to get this one member. And then we can have a fun argument about what, do we need more than that? Are there any things besides the x's? But there's no way we can do it with a finite number. So this is an infinite set that is linearly independent and may span the region, but certainly we can't span the region with a finite set. And again, I'll put a little question mark here simply because we haven't covered in any systematic way the infinite properties or infinite sets, so we would need to be super careful about any logic. But there's strong evidence here at least that a finite set will not span the C infinity. So that cannot span C infinity, and so, finite set. And so if we get where a finite set cannot span C infinity, we're not going to get a basis with a finite number of elements.